Transplantation at Mayo Clinic in Florida. He is also the chair of the Mayo Clinic Enterprise Transplant Specialty Council. He joined the staff of Mayo Clinic in 2007 and holds the academic rank of Professor of Surgery, Mayo Clinic College of Medicine and Science. He earned his medical degree at Hacettepe University Medical School, Ankara, Turkey. He then completed an internship in surgery at Lincoln Medical and Mental Health Center in New York, and a residency and chief residency in surgery at Mayo Clinic. He subsequently completed a fellowship in transplantation surgery, also at Mayo Clinic. His clinical interests are in liver, kidney, and pancreas transplantation, process improvement, and resource utilization in transplant surgery. He constantly publishes in high-impact scientific journals and has health reviewer responsibilities for prominent publications. He's been leading innovation efforts in organ transplantation field since 2018. He chairs Mayo Clinic's Transforming Transplant Strategic Initiative. In recognition of his work, he's received many awards and honors, including the Care Key Guard Award for Outstanding Research Achievement conferred by Mayo Clinic. He was also recognized with the Young Investigator Award awarded by the International Liver Transplant Society. He has numerous memberships, including American Association for the Study of Liver Diseases, American Society of Transplant Surgeons, American Society of Transplantation, and the International Liver Transplantation Society. The floor is yours, sir.
Thank you very much. Thanks for inviting me to give this talk. As you mentioned, I'm a transplant surgeon, so the talk does not have much of a data actually, but it gives a perspective of what we face in today's organ transplantation. I'm going to take you through the evolution of organ transplantation during my talk, and I'm going to pose the question of how can we change the current organ transplantation world by collaborating between the clinical work we do and with Terasaki Institute. So these are the learning objectives of this talk. We're going to identify the milestones of organ transplant evolution, understand the current organ transplant practice. I'm going to mention about the shortcomings of organ transplant practice and implications to patients who are in organ failure. And then we're going to talk about the innovative solutions that will affect the patient care and organ failure and transplantation in the near future. There are two main parts of this talk. In the first part, I would like to define the problem that we clinicians in transplant field face every day. Many of you in the audience may not be familiar with the organ transplantation, the difficulties that patients with organ failure go through, and the uncertainties that they face starting with the diagnosis of organ failure. Defining the problem is important to ultimately evolve the discussion towards why medicine and basic translational science will need each other to find solutions. You will see that I will be focusing on the problems more during the talk, and understanding the problems will ultimately lead us to being creative in finding the solutions. As a disclosure, again, I'm a clinician. I take care of patients with organ failure. I'm a surgeon performing organ transplants. For my views are from the pure clinical angle, but I'm convinced that medicine and translational science need each other to find solutions. As an important background information to set the stage, I need to start with this slide. Organ transplantation is performed to treat patients with organ failure. This could be heart, lung, liver, kidney, pancreas transplantations. Those are the most common ones. It's very important to emphasize that organ transplantation depends on organ donation. In other words, organ transplantation does not exist without organ donation. And in the current system, the organs come from two different sources, either from patients who are declared dead or dying, or from living donation. In the United States, most of the organ donation is from deceased donors, and some of it come from the living donors. It may be very ironic that to be able to do a transplant to save a life, we wait for someone to die so they can donate the organs. So we essentially wait for a tragedy to happen somewhere in the country, and then so then we can transplant our patients. Considering the long history of medicine, organ transplantation is a very new medical field. It was only in 1954 when the first successful kidney transplant was performed in a patient. In 1967, the first successful heart and liver transplants were performed. And I have to mention that all these successful first transplants were preceded by many unsuccessful trials during which surgical and perioperative details were ironed out. Until 1968, we did not have a definition of death. Does that happen when the heart stops working, or does that happen when the brain stops working? In 1968, an ad hoc committee at Harvard Medical School published a pivotal report to define irreversible coma. And these criteria gradually gained consensus towards what's now known as the brain death criteria, which then led to the Uniform Determination of Death Act that was accepted by the US Congress. Since then, both medical and legal communities in the United States use brain death as a legal definition of death, allowing a person to be declared legally dead and be able to donate organs while organs are still viable in the body. But it wasn't until the 1980s when the organ transplant moved from a more experimental field to a reality, clinical reality, that could truly help thousands of patients with organ failure. Looking back, 1960s and 1980s emerged as the 2 decades that many of the developments helped this new field of medicine. In fact, the very first transplant programs in the United States started opening in the early 1980s in our lifetime. In 1970s, it seems like a decade of big gap, but however, behind the scenes, there were a lot of scientific and technical activities that are happening, which paved the road to successes in 1980s. So with the US Congress's passing of the Uniform Determination of Death Act in 1981, a comprehensive and medically sound basis for determining death in all situations was established. This, in turn, provided legality for organ donation. And with the discovery of modern medications in the 1980s to keep the immune system in check, a new era opened to keep transplanted organs functioning longer periods. Until the 1980s, we did not know how to keep a donated organ safe outside of the body for long periods. With newly developed organ preservation solutions, for the first time, we were able to keep these organs safe outside of the body for long hours, which allowed us to transport these organs from one geographic location to another. And finally, we established an organization in the United States to oversee the processes to allocate donated organs to patients in need and also evaluate individual transplant centers' performance and compliance. As a result of these developments in the 1980s, organ transplant practice became a common, accepted, and growing medical field. So this whole thing happened in our lifetimes in the last 4 years or so. With the experience gained throughout the world in the last 4 decades, transplantation started moving from a solid organ transplants to transplanting other body parts. As you can see in this list, we're able to transplant many different parts of the body. These practices are small in scale. They combine expertise from other disciplines such as plastic and reconstructive surgery with expert contributions from transplant. They will likely remain in small scale due to low demand and high technical difficulty of these procedures. And if we take a step back and look at the success of clinical practice and transplant, we can recognize that there's patient need. We can transplant any organ, technically. We can use marginal organs, the infected organs, successfully, and we come out with successful outcomes. We can provide safe care in the time period before the transplant, around the time of transplant, after the transplant, and many of these patients live very long and successful lives after the transplant. And then we can now prevent rejection, infection, and then we're much better with organ selection and matching. And then, in fact, back in 1980s, when the practice became prevalent in the United States, the 1-year survival after liver transplant was only about 70%. Now, it has clearly approached 95% in many of the transplant programs. And if you look at the broader statistics, how we have been able to help patients with organ failure, there are a lot of success stories. In fact, more than 1 million of these stories. Between 1988 and 2022, 1 million solid organ transplants were performed in the United States. And every year, we're now performing more than 40,000 transplants. And considering the complexity of these patients with organ failure, the need for many medical surgical specialties involved in taking care of these patients, complexity of the organ allocation, the matching, logistics, this is a major achievement. And this points to the organizational success. For those institutions with transplant centers, it's an institutional success. For those of us practicing organ transplant, there's nothing better to see a very, very sick patient receiving an organ transplant and then coming back to see us a few months later with their families. So there's a lot to celebrate in organ transplant world. Over the last 3 decades, the number of organ donors increased. That's good news. And this is related to education of population, education of healthcare professionals, and better organization across the country. And the fact that population understands organ donation saves lives, at least in the United States, population is very generous and they donate organs. And this really helps increasing the organ transplantation for those patients who are in organ failure. But there's the other side of the story, and that is more patients are waiting for organ transplants. Importantly, we're seeing increased number of patients with organ dysfunction and failure because we have gotten better in recognizing and diagnosing organ dysfunction and failure. And if you look at the picture from this angle, you could easily say that this is potentially a failure because we're not able to help each and every patient. There are more than 100,000 patients waiting for organ transplantation. This is an organizational failure, this is an institutional failure, and this is a technological failure. We're not able to help everybody that needs an organ transplant. I already told you that there are over 100,000 patients waiting for organ transplants, and then some of the data suggests that how hard the centers are working to transplant patients in need for organ transplantation. In this picture, you can see that there were over 18,000 organ donors, which shows how generous people are in donating organs in that time period. But at the same time, we added close to 60,000 patients to the wait list for organ transplants. Instead of closing the gap between the patients needing organ transplants and then having more available organs, the gap actually widened. We're essentially chasing our tail to transplant more patients. And so there is a demand and supply discrepancy if you look at from this angle. And if you look at this data, actually, one of the biggest problems is that as people are donating organs, American population has been very generous, and we are actually not able to use every organ that is donated. In fact, if you look at the discard rate over the last several years, the organ discard rate increased significantly. And even though the people are donating their organs, we're not able to use those organs successfully with the fear that the organ quality is not good, or we find there's some issues with the organs, and then we're not able to actually successfully transplant them. We put them in the trash, which is a tragedy. And that's related to the organ quality issue. So there's a problem that we face. One is that aging population. And it affects us in several different ways. One is aging population is relevant to both on the donor side and for the recipient side. In the recipient side, we are seeing increasing number of patients with organ failure. As we age, our organs start failing. On the other hand, those people who are donating organs where they are actually older. So that means they're decreasing quality of donated organs. As I showed in the previous slide, those organs, some of those organs were not able to use them successfully. We discard them. And then those organs that we are able to use that come from older donors, they are either failing prematurely after the transplant, which means some of those recipients actually will need repeat organ transplants, or then we're altogether not able to use some of those organs, we discard them. And then eventually this whole circular movement means that there's an increasing demand for organs. That is the reality in the current system. And then another problem that we face is that the medicine is all fields are getting better, which means we are actually diagnosing organ failure in a much better way. And then the patients have better medical access, which means that there's an increased access of those patients to medical care. And then the population of patients with organ dysfunction and organ failure are constantly increasing in the United States. So that means demand is altogether increasing. And then another fact that we need to mention is that even though we have gotten much better in medicine, we think that medicine alone cannot find the solutions. That means there has to be a collaboration between medicine and other fields to be able to create solutions. So if you look at today, and then if you consider what's going to come in the future, one, we don't necessarily know how many patients are in organ dysfunction. That data doesn't exist, where we can only estimate because a lot of patients, unlucky patients, they don't have access to good medical care. Number two, we don't know how many patients with organ failure are never considered as a candidate for organ transplant. Again, that could be the access to the good medical care. Excuse me. And then we also don't know how much more we can do to increase organ donation. And organ donation never caught up with the demand. And then we don't know if we've ever caught up with that. And we also don't know the cost of the organ failure, organ transplant, and post-transplant care to society. Organ transplant is a very expensive procedure. And we're not only talking about the surgical part of the care. These patients require a lot of care before and after the transplant. And this is a lifelong care that we have to provide. So when you consider those more than 100,000 patients waiting on the wait list for organ transplants, we think that it could be the tip of the iceberg, actually. The real numbers, if you consider every patient with organ failure, this could be probably 10 times more than that. And as you would understand, this is not a sustainable model. We will always lose if we don't increase the either supply or decrease the demand for organ transplants. So there's an unmet patient needs. There are increasing number of patients with organ dysfunction and failure. On the other hand, there are limited availability of transplantable organs. In this country alone, 20 patients die every day while waiting for an organ transplant, while at the same time we discard more than 5,000 donated organs each year due to poor organ quality. In order to design the future, we must first face today's problems. In the current state, transplant practice still depends on organ donors. If there's no organ donors, there's no transplant in the current system. It's really worth emphasizing that fact because it really affects us transplant physicians on a daily basis. We see patients die on the waiting list, and we can't really do anything about that. People donate organs, however, not all donated organs can be transplanted due to quality issues. Transplant still depends on anti-rejection medications, and these medications have side effects, including causing further organ damage. And whether a patient will definitely get an organ transplant is never clear. We cannot guarantee an organ to a patient. And when we talked with the patients, we made it clear that there's a chance that they may die waiting for an organ transplant. And it's very unpredictable when a patient will get an organ transplant. The whole system depends on a tragedy happening to someone somewhere. And so the families can donate the organs. And having an organ failure, waiting for transplant, and transplant procedure itself and the post-transplant care are very, very costly, not just to the individual patients, but to the whole society. And the organs that we transplant may not last a long time, and some patients will need repeat transplants. So we created this system in 1980s, and then we have become prisoners of the system. What will future of organ transplant look like? Instead of waiting passively to see if someone is going to do something about the problem, the better question is, how do we create that future? And how do we play an active role in shaping the future? Instead of waiting passively, we wanted to take an active role in shaping the future of organ transplantation. Organ failure will not go away, but we have to do something innovative to address the existing issues. And if we set our starting point as no patient should die waiting for an organ transplant, we need to address two sets of problems. If we take a step back and look at the picture, we realize that major part of the issue is a supply and demand issue. There are increasing number of patients with organ failure. On the other hand, there is limited supply of organs. Systematically thinking, we need to decrease the demand and increase the supply. In order to decrease the number of patients with organ failure, we first need to prevent organ failure from happening. And for those patients already received organ transplant, their new organs may not last a long time, and they may need repeat transplants. So for those patients, we need to prolong the longevity of the transplanted organs so the donated organs are used for the first-time transplant candidates. On the other hand, we need to increase the supply of organs. Those organs that are deemed inferior quality in the current system, can we make them better with technology? This will decrease the chance of discarding them. And of course, the most difficult one is, can we liberate ourselves from the dependence on organ donation by engineering new organs using technology? This is not an easy task, but that's the goal that we should pursue in the next several years. The future that we imagine is such that we decrease organ dependence on organ donors. We will refurbish less than optimal organs by custom designing organs. We will avoid immunosuppressive medications. By having more available organs, ideally, every patient who needs an organ transplant gets an organ at the optimum time with decreased cost to society, and these organs will have long lives. That is the future that we imagine. Mayo Clinic has 3 campuses. I happen to function at the Jacksonville campus. Each of our campuses has very large transplant programs. In fact, Mayo Clinic altogether is the largest organ transplant provider in the country. We've done more than 34,000 organ transplants at Mayo Clinic. That's by far the largest number in the United States and perhaps in the world. And then each year we now do more than 2,000 organ transplants, and each of our campuses are connected. We use the same patient protocols with the same or similar outcomes. In 2018, we started a major research and innovation project at Mayo Clinic to address shortcomings of organ transplants. We call it Transforming Transplant. That's the name of the project. There are actually 4 goals of the project designed to address the problems that I summarized in the previous slides. Restoring donated organs, so then optimizing organ to have the best outcomes, and then we're hoping to decrease organ discard rates. Number 2, we would like to prevent graft failure in patients who received organ transplant previously. So then we aim to have 1 organ transplant for 1 patient, and that patient will live their normal lives and will not ever need a second transplant. The third one is, can we prevent organ failure from happening by diagnosing organ dysfunction in a timely manner, that we do something to prevent organ failure from happening. At least in some subset of patients, we can prevent organ transplantation. And then last, but the most difficult one is, can we engineer new organs? When a transplant is needed, we eliminate the uncertainty of organ donation, eliminate wait times, use custom-made organs, and then perform organ transplants at the optimal time. The project requires us to increase collaboration across our institution, but importantly, it requires us to build new collaborations outside of Mayo Clinic. So we're fortunate to form these collaborations to use expertise from different institutions like Terasaki Institution. In the next several slides, I'll walk you through some of the next new technology that is progressing in the last few years. As it turns out, the restoration of donated organs may be technologically relatively easiest of all solutions. Going back to talking about the organ donation, the field is moving from older technology to more sophisticated technology. And between 1980s and about 2020s, we were using this primitive technology of organ recovery, preserving in the cold specialized solutions, cold storage, and transporting to transplanting programs. In the last several years, ex vivo machine perfusion technologies became available, and we're increasingly using these technologies to our advantage. In fact, if you think about the how we stored the organs before and how we're storing and transporting those organs, there's a huge difference in the technology, and that allows us to be more successful. Believe it or not, the beer cooler was the most used gadget that we use in organ transplantation in the last 4 decades. Now we're using to more sophisticated technologies. In fact, the underlying technology is moving from more passive static storage and transportation of the organs to more active dynamic storage of the organs that will allows us to keep the organ outside of the body for longer periods, and allows us to be more successful after the transplant. Another way to look at that is organ preservation moved from whole organ preservation to more cell organelle preservation with the new technologies. Thinking about the technologies, you have to consider what we have now, actually. These new technologies allow us to really adjust the logistics of organ transplantation. Transplantation has always been an emergency surgical event. Because of the nature of the emergency surgical event, there are high personnel expenses related to nighttime and weekend staffing. There's high stress levels for the transplant teams, patients, and families because of the uncertainties around the transplant. And then, of course, there's increased burnout in transplant surgeons, which decreases the longevity of how we function as teams. And some of the existing issues are obviously organ supply, organ demand discrepancy, the rising age of the donors, decreasing quality of organs that I mentioned before, and then increasing number of the marginal organs, such as donation after circulatory donor organs. They deem to be considered inferior. Now we're essentially seeing more of these organs. By using the technology, we're able to actually bring the outcomes very similar to the best organs that are donated. And desired future practice using these technologies could be, can we use all donated organs? And can we transplant every patient that needs an organ transplant? And then importantly, can we do the timely transplant before a patient with organ failure becomes very sick and the recovery period becomes very problematic? And what we want is that we want best outcome for the organ transplant recipient. We want the best outcome for the transplant programs, and then we want best outcome for the transplant teams by increasing their longevity in transplant. And of course, with these new technologies, we want enough time for organ assessments, not just a singular time point where we can say yes or no, but it gives us more opportunity to assess in a longitudinal way so we can actually do something to potentially make the organs better. And we need enough time and appropriate technology to monitor an organ outside of the body. And then these new technologies will allow us to work on the logistics of patients coming to us from different locations in the United States. Obviously, the United States is a big geography. There are patients in every state, and then bringing them in a timely manner to transplant programs is important, and these new technologies are allowing us to do so. So these are the ex vivo machine perfusion systems available for all solid organs, heart, lung, liver, kidney. And some of them have already cleared FDA approval and are clinical use. Others are going through clinical trials. By achieving organ assessment and organ improvement, the potential effects of using these technologies is to increase transplant rate, decrease mortality on the waiting list, and increase ability to transplant patients at earlier stages of their disease process. From the many past patients that we transplanted, one big lesson that we learned is that the better condition the patient goes to transplant surgery, the better the outcome is in the short term and in the long term. So that means timely transplanting these patients before they get really sick and their other organs start failing. And then by doing so, by doing the time of transplants, that also decreases the cost of care during the wait period and also in the post-transplant recovery period. Some of the logistical challenges, obviously, are some of them are unique to the United States because of our geographic area, the geographical distance and travel issues that we deal with. There are also issues related to how do we get these organs safely and who recovers those organs from the donors. And then do we have qualified perfusion teams available that can recover the organs and then place on the machines and then safely transport those. And then obviously, as the transplant numbers will increase, are we going to be able to accommodate by increasing our staffing models to do more transplants? And then some of the other logistic issues related to the hospital business, like operating room availability, and then being able to find operating room at any time point during the day and during the night. Some of the logistical helps that these new technologies provide is that now it used to be a rush through transplant surgery. Now, because we know that the organs are on the machine, we can actually take time and do a safer surgery. And we can actually transplant multiple organs to a single patient. Many patients now come with multiple organ failures, and we're able to do that without the restrictions and time. And we're able to accept organs from faraway places that wasn't thinkable before. And then we can actually bring patients from different locations to our transplant centers. And then because this increases the flexibility of timing, we can actually optimize the medical condition of the patient before going to the surgery. So then the outcome will be much better. Some of the unique things about the machine perfusion is that if you think about the issue related to control of an organ outside of the body and being able to monitor that, it gives us a opportunity to modify the organs. Right now, we're using these machines in a primitive way to buy us some time, but it really allows us to modify the organ outside of the body. And I think this is the future area that we'll see a lot of progress in the next few years. And some of the potential areas that can be done is ischemia or perfusion injury prevention, immunomodulation of these organs, and some of the cellular and acellular therapies like infusing extracellular vesicles to improve the organ function. There could be infusion of anti-inflammatory agents to help with the microcirculation and endothelial protection. And there could be therapeutic agent infusion to decrease the microbial transmission from these organs. And obviously, an example here is for the liver. Some of the livers come as fatty livers. Can we actually decrease the fat content of the organ? We're able to keep these organs for several hours or several days outside of the body, and then that will give us more time to work on some of these issues. One example of keeping an organ outside the body in a functional way came from a Switzerland group. This was published about 5 years ago, and this group kept liver donated liver outside of the body for 1 week. Actually, at the end of 1 week, they still had function in that liver, and they had intact the liver structure. To give you an example, a comparison example is that with the cold perfusion and storage without the machine perfusion, the maximum lifespan of a liver is about 12 hours, actually. So now we're talking about total paradigm shift in terms of keeping these organs outside of the body with these machines for a very long time. And obviously, other than optimizing the organ and the recipient, it really opens up a lot of new opportunities for us to make an organ better. The other two areas that we can address regarding the main shortcomings of transplant practice is to find solutions to identify organ dysfunction early, so then we can prevent or reverse progression of the disease process, as well as finding ways to prolong lifespan of organs already transplanted so that these recipients do not need repeat transplants. While transplant professionals are dedicated to patients and organ failure and transplant recipients, we all need to recognize that organ failure in a patient is also our failure, us in medicine. Somehow, we do not have all the tools, information, and answers and then we let an organ fail. I believe finding solutions to stop and reverse organ dysfunction should be one of the main goals of our mission. And for those who already received and destined to receive organ transplants, it should be our goal to prolong the life of those precious organs that were donated and transplanted. Similar to other areas in medicine, continuous monitoring of patients from remote locations can provide information to understand disease processes. This then allows us to develop care plans and timely interventions to stop and reverse disease process, as opposed to today's intermittent care in which patient touch points are predetermined or scheduled, or when symptoms arise. Remote patient monitoring may allow us to have more continuous care. Increasing data points will likely increase our understanding of pathophysiology of a disease, and understanding the disease process can open doors for more personalized approach. This approach will ultimately affect outcomes for our patients. The last area has been evolving is engineering of new organs. This is the most difficult area. May take some time to see all efforts come to fruition. One way to engineer new organs is tissue and organ printing. This area is very difficult because organs are three-dimensional structures with multiple different cell types in a single organ. The cell location in each organ and overall architecture could be very different. The architecture may affect interaction of cells with each other to have functioning organs. And also some of the organs, such as heart, have more mechanical function as opposed to liver, which is an organ with more biochemical responsibilities. And having all these complex issues, the vision is to be able to create new organs using patients' own cells, optimize fabrication, and custom print organs to fit specifics of that particular recipient. And this will potentially allow timely transplantation before patient gets very sick, And if we're able to use patients' own cells, it allows us to prevent using anti-rejection medications that suppresses the immune system in the long term. And if you think this is science fiction, I can tell you that this is rapidly becoming reality in the very near future. Parallel to 3D printing technology, using decellularized scaffolds of organs from animals is another option. These animal organs can be bleached of native cells and recellularized with patients' own stem cells. Because patients' own cells are used, it eliminates the need for lifelong immunosuppressive medications. And this technology is also moving rather rapidly. There are indications that several companies are working in this area. And on the right hand, you can see the decellularized lung lobe at the top, and then the same lung lobe cellularized with human cells. So this will become a major source for organs in the future. Many of you in the audience may have recently seen the news that organs from pigs have been transplanted in human patients. Xenotransplantation is transplanting organs from animals to humans. And the idea of xenotransplant has been around for many, many years, and it is becoming a reality in the very near future. In fact, FDA approved a clinical trial for human kidney xenotransplantation just about 2 weeks ago. And that clinical trial will start this year, very soon. This is made possible by decades of progress, and then by adding and removing genes, genetically altered pigs are raised and their organs are used for transplant. And some of the initial work in the 1960s and later 1980s were done in primates. However, pigs offer some advantages over primates. They're easier to raise, they reach maturation faster, and achieve adult human size in about 6 months. And these most recent examples, 10 different genes were modified in pigs, 4 porcine genes were knocked out, and 6 human genes were knocked in, which allowed us to use these organs successfully in human patients. And it's if successful, if the clinical trials were successful, this will potentially supply us with unlimited number of organs, which will liberate us from dependence on human organ donation and all the uncertainties related to human organ donation. So then, if you think about all the technologies and the cost of the technologies, biomedical engineering is not cheap, actually. But you have to consider the cost and the value of what we do in medicine and in translation research. So not everything is cost. We have to think about what value it brings to the society. And if you look at how you calculate the value, you essentially calculate the quality and services divided by the cost, essentially. And then some of the quality metrics that we always have to consider is, one, survival before and after transplant, the life quality of the patients before and after transplant, if they receive transplants or if they don't receive transplants, and obviously some of the metrics like return to work or being living a productive life. And if you also consider the cost of what we do, obviously transplant is very costly. But by transplanting patients when they're relatively healthy, this could potentially decrease the cost. So that will potentially increase the value of what we bring to these patients. You have to also consider the access to care, actually. As I mentioned, we are not able to transplant every patient. And because transplant is still very limited in the United States and the rest of the world, there's an issue related to access to care. Many patients are not even considered a transplant candidate before even they step into transplant centers. There's a sort of a mental limitation restriction that happens that when a older patient has organ failure, they're not even considered to be sent or referred to the transplant centers. So by increasing the availability of the organs, by increasing the quality of the services that we provide, we actually secondarily increase the access to care so we can help more patients. So that's the ultimate goal. The organ transplant really started with the pioneer surgeons in 1960s, and it evolved over the last several decades. And again, considering the long, long history of medicine, it's a very, very new field. In 1960s and 70s or 80s, the surgeons quickly realized that these patients that are being considered for organ transplants are very complex and need extensive and longitudinal medical care. So we really added internist anesthesiologists to our team, so it became more than a surgical practice. As the complexity of the patients and the system evolved, we then added critical care physicians, organ procurement specialists, quality compliance personnel, and this all happened around in 2000s. And as we envision the future, we envision that clinical transplant teams has to be working side by side with translational scientists, engineers to bring innovation to clinical practice in an accelerated fashion. So bench to practice approach will accelerate, and the timeline between bench to practice will shorten. And none of us has crystal ball to predict how exactly the future will look like. The prediction is that transplant will still be here in the next several decades, but perhaps it will look much different. We'll be widely utilizing regenerative technologies, individualized medicine, and biomedical engineering for our patients. And rather than working in parallel paths, these entities will have to continuously interact with each other to be able to advance innovation. There's no simple line that will take from one step to another. There has to be a continuous interaction, asking tough questions, and then developing new projects to be able to achieve our goals. And I showed this slide at the start of my talk. It gives the impression that the path from problem to solution is a single, straight, and easy. In reality, none of what we do in clinical medicine and biomedical engineering is simple, straightforward. And there is a constant dynamic of problems and solutions. As we resolve one bottleneck, we discover another bottleneck. Regardless of difficulties we face, progress is better than the stagnant state, obviously. And then my personal thought is that, one, as you learn more about the field, we realize that we don't know everything, that the problems are not solved in silence, and medicine will not solve the problems alone. The traditional academic structures may not solve the problems, so that really opens up a need for collaboration. And then team science is always superior to individual efforts. And then at Mayo Clinic, we're promoting these principles. With that, I will stop and try to answer your questions. Thank you.
Thank you for this talk, Professor Tanner. A question came in. Will xenotransplantation address organ shortage in the short or long term? When do you think it will become a reality?
Thank you for that question. It is becoming a reality, actually. So it's starting with the xeno kidney transplants. And FDA about 2 weeks ago approved a clinical trial for 2 different companies' products. And those trials will start this year. And we're hoping that Mayo Clinic will be part of that trial. And the biggest need for organ transplants in this country is kidney transplants, and that's why it's starting in kidney transplants. But we suspect once we prove that this is a successful way, we can do it in other organs also.
Thank you. What are the major challenges for the clinical adoption of xenotransplantation, and how can we accelerate this process?
Yeah, the simple answer is it's a new area, and we don't know what we don't know. There are a lot of unknowns in xenotransplant because these organs are coming from animals. There are obviously major immune issues. Even though we are able to change some of the genes in these organs, we will still deal with long-term issues. Number two, we don't know how long these organs will last, actually. The longest surviving kidney transplant from a pig to human has been alive for about 2 months, actually. That was transplanted in late November. That kidney is still working. But we don't know that that kidney is going to last 2 years or 20 years. So unless we do the clinical trials, we will not know, actually. And then the third one is there are obviously some issues related to potential disease transmission from animals to organs. And we don't know, what type of disease will eventually transmit. And we don't know if there will be treatment options for those. And we don't know if they're going to be dangerous to not only to that patient or to the surrounding population also.
Thank you. Great talk. Why is the transplant timing uncertain and unpredictable?
Because we wait for an organ donation, actually. And that is a reality. If you're a patient waiting for a liver transplant, you actually get evaluated by a transplant center. If you pass all the tests, you get placed on the waiting list and you're started for waiting for a liver transplant. From that on, it's unpredictable when you're going to get a liver transplant because, again, we're essentially waiting for a tragedy to happen. Somebody dies, and then the family donates organs, and then we accept those organs and then use it for you. So it's very, very unpredictable. And we have absolutely zero control of who dies out there and who donates the organs. And that's a big tragedy, actually. So every time you get an organ offer, you're actually celebrating that you're going to get your transplant, your patient get transplanted, but then the other side of the picture is that, well, somebody died, so you're getting that organ actually. And that is the reality in organ transplant in the current system.
Thank you. Thank you so much for a great talk. What do you think the main role of data science is going to be for organ transplantation over the next 10 years?
Yeah, that's a very good question, actually. Because these patients become our lifelong patients, we accumulate a lot of data, actually. There's a lot of longitudinal data from the time when the patient is getting evaluated all the way to several years after transplant, actually. So when you accumulate all that data, that gives you power to look at the data to determine, one, the trend of how fast the organ will deteriorate, and also how the patient does in the long term, actually. So using, big data, that will be very important to one, determine who's going to do well versus who's not going to do well, who's going to have rejections versus no rejections. And then you can develop new systems to really address or prevent problems from happening.
Thank you. What are the main challenges in achieving the best outcome for the recipient, program, and team?
The major challenges is much different than what we were experiencing in 1980s, actually. In that time, transplant world was very, very new, and we didn't necessarily have all the tools and gadgets to one, determine rejection. We didn't have all the good medications to treat rejection or prevent rejection. So most of those are actually gone. So for the most part, organ transplant has been very, very successful, to the fact that we think that the organ transplant has become a commodity, actually, meaning that the results are very similar across the board if you look at all the transplant programs. And what are the current challenges? Again, the current challenges is, are we going to be able to transplant more patients who are in need for transplant? I think that's the major thing. Because again, we're seeing just the tip of the iceberg. We don't necessarily know how many patients are having organ dysfunction, and we don't necessarily know how many patients die with organ failure. A lot of patients, they don't get access to a transplant center, they just die at home. Many of those patients die with organ failure. And that is the biggest challenge, of course.
Thank you. The fabrication of complex human tissues and organs is still in the developmental stage. How do you think recent research advancements are improving the quality of life, and where do you think additional research should be focused to enhance this process further?
So maybe there are two parts of that question. One is, tissue engineering and how easy or how difficult that is. How difficult that is, I can, tell you, tissue engineering is very difficult. And when you think about a liver, it's a three-dimensional structure with many moving parts. It's not really like a building, a building where the, structures will stay stagnant and then your right hand wall is not going to interact with the wall down the hallway. Actually, these are living tissues. Actually, each and every cell will interact with each other and will continue to do that, and we'll have to do it with some discipline. Actually, you can't have a out of control interaction between the cells. So that is a very difficult goal to achieve. How do you make sure that you are actually putting the cells in the correct places, and those cells will actually get used to their new environment and will start interacting with each other and be functional. And that is a very difficult, goal to achieve, obviously. And then the second part was related to
Additional research to enhance this process further.
yeah. Again, this is a very difficult project to handle at any single institution actually, and this really requires a widespread collaboration across the board, because I'm not aware of any single institution that has all the expertise that can accomplish a sort of a 3D printing of an organ. This requires cellular engineers. This requires immunologists. This requires tissue engineers. This requires expertise in vascular biology, and all kinds of different expertise, and really requires people getting together to really achieve this goal.
Thank you. One final question. Does 3D organ bioprinting offer better chances than xenografts in terms of timely availability as well as reduced rate of rejection?
Maybe there are two different ways of answering that right now, because xenotransplant is ahead of the 3D printing of organs. Obviously, xenotransplant is getting to clinical trial stage. It's ahead actually. So in the short term, this may be a viable option. But then again, as I mentioned before, there are a lot of unknowns about xenotransplant. So at some point, we may start seeing problems. In the long term, both could be viable options for patients. Obviously, you don't want to put all your eggs in the same basket, but I think investment in developing those two technologies will be very important.
Thank you. One final personal question. Is the US who's the world leader in transplantation? And what are the latest, there's this, transplant from the pig. Are there other places in Europe or Japan are doing interesting work?
So Europe has done a lot of work on machine perfusion, actually. They're ahead of the United States in machine perfusion technologies. And that's because of the scarcity of organ donors in Europe, actually, and the aging population, and they had to really create new solutions to be able to use every donated organ. And that's why they're probably about a decade ahead of United States. In the Asian countries, especially China is showing a lot of interest in new biomedical engineering technologies, actually. There are some studies that are done on xeno organs also, but none of them has come to clinical trials yet. And none of them has actually crossed the Pacific Ocean to get to United States yet.
One final thing, is this organ transplantation a developed rich country solution? How about the people in other places like Africa, India, or etc.?
Yeah, that's a very good question, actually. When we talk about access to organ transplantation, we shouldn't assume that we're just talking about the United States population. Obviously, you're absolutely right. I think sort of a democratization of these technologies to help the global population will be the ultimate goal for us. But because these technologies are very expensive, because organ transplant is currently very expensive, I think the progress will start in the first world countries, to be honest. But ultimately, it's obvious that the third world countries are having a lot of organ failure, organ dysfunction also. And then, these technologies will get to those countries hopefully in the next 1 to 2 decades.
Thank you so much for the fantastic talk and question and answer session for us. Thank you for your time.
Thank you.